or you'll use the sum and difference identity to solve trig equations. But sum and difference, let's talk about. The first one they teach you is the cosine one, oddly enough. I don't know if they do it like this, but this is the way I like to do it. And the cosine one is easier to remember because it starts out cosine, cosine. And it's got to be cosine of A times cosine of B. There's no other combination you could use. The next is the opposite of what this is. So instead of plus minus, it's minus plus. And then we know that these sum and difference have two sines and two cosines in them. So this has to be sine of A, sine of B. And then the sine, I mean, if you're staring at these, it's better if you're not looking at it. Whenever you're trying to memorize something, it's better to not have it in front of you and test your memory. You know what the sine is?
Yeah, isn't sine A cosine B, and then it's the same as the sign in the parentheses, so it's plus minus. Cosine A sine B?
Yeah, I prefer to maintain the order because I know this has got to be different than A. In other words, this has got to be B. Yeah, so it's just the reverse. And notice there's two sines and two cosines in it. All right, and then tangent, did they make you memorize that one too?
Yeah.
Tangent's actually pretty easy to memorize. It's tan of A times the tan of B.
And then it's divided by something.
1 opposite minus plus.
Isn't it tan A, tan B again?
Yeah, I did that wrong. I didn't memorize it very good, did I? I think you're right. The tan A, tan B is in the denominator. And
I think tan B is just at the top.
Actually, I think it's plus.
Here, I'll check. I have it right here written down somewhere in my notes.
Tan A plus tan B in the numerator.
Let's see. Tan A plus tan B. Double angle identities.
It's before that.
Yeah, we want. Yeah. Oh, there it is. Okay, so it's tan A minus tan B on the top. And that, that's if, so it's the same sign. Yeah, it's plus minus, so it's the same sign.
So the numerator is plus, though, right?
Yep, so the numerator would be the same sign as the parentheses, and the denominator is the flip sign of the parentheses.
Right. In other words, if we had A plus B, this is it. If we had A minus B, my numerator is still tan A plus tan B, right?
No, if you had tan A minus B,
okay. So
it would be,
I need a minus sign there is what you're saying.
Yeah.
That's the correct identity. It's been a while since I've done the tan one. So, yeah, so the numerator, it's the same order, and the denominator, it's the opposite order.
Yeah.
All right, so what specific problems are we going to apply these to?
We're starting out with kind of like degree problems, or radian problems.
That's fine.
So
we can do radians just as easy as degrees.
Yeah. So it says find the exact value of each trigonometric expression.
Okay.
So the first one is tan of 23 pi over 12.
Now notice that that's not a common angle, but it is an angle that's in the unit circle. In other words, the unit circle goes up to 2 pi, which is 24 pi over 12. So we're barely inside the unit circle. Okay?
Okay.
So we want to break this up into the sum of two angles or the difference of two angles so that I can write it like that. Well, what two angles are going to add to 23 pi over 12?
This is where I had trouble. When I had this problem, I had to convert it to degrees.
Yeah.
I have a hard time seeing the radians.
You're not the only one. I'm kind of with you there. So what is this in degrees?
In degrees, it would be...
It's got to be
23 times 180 divided by 12, 345.
I was just going to say, doesn't it? It's pi over 12 short of being a full circle, and pi over 12 is 15 degrees. So 360 minus 15 is the quick and dirty method of doing it. Now, that's probably going to be easier to figure out a solution. Let's see. 330 doesn't work.
365, 330. Could you do 315 plus 30 degrees?
There you go. No, because we don't know 315. Yes, we do. Yeah.
Yeah, 315.
Yeah, that is a common one. Yeah. So we're going to write it like this. Okay, good. All right, now let's put it in directly into the formula. Tell me what to write.
It would be tan 315 plus tan 30 over 1 minus tan, 1 minus tan 315 tan 30.
Now let's fill it in. What's the tan of 315?
315 is...
Notice that we don't ever have to go back to radians. In other words, we convert it to degrees, which is just fine because our answer is going to be a number.
I just have to think about the which is over which. 5 pi over 6 would be 1/2 the cosine, root 3 over 2 is the sine, so it would be root 3 over 1.
For the tan of 45 degrees? Remember, that's all we need is the tan of 45 degrees, right?
Wait, but for for 315?
That's a reference angle that's 45 degrees. In other words, when you find an equivalent first quadrant, you're subtracting 360 minus this. So we're talking about a 45-degree angle whose tan is 1, but it's in the fourth quadrant, so what's its sine?
Its sine is 1. Well, it's tangent.
Negative. When I say sine, I don't mean sine cosine, I mean SIGN.
Sorry.
So minus 1 is what the tan of 315 degrees is. Now, what's tan of 30? And I really think it's, rather than doing it the way you did it, even though it works just fine, you're always ending up dividing a fraction by a fraction when you have sine over cosine. Rather than do it that way, draw the 30-60 triangle and take the tan of 30.
Okay. That comes out to be root 3 over, no, 1 over root 3.
Okay, now tan of 315 was minus 1. And always, I would always do it this method right here. In other words, fill in everything. Do not try to save time by skipping or by combining steps. In other words, it's real easy to make a mistake here. You'll notice I got two negative signs in a row. I got an irrational denominator. I got all kinds of things that could throw me off here.
Yeah.
So what should I do next? If I'm trying to come up with a single quotient, in other words, a single ratio.
You could multiply -1 by 1 over root 3, getting -1 over root 3. And then if that's being...
Hold on.
Sorry?
Hold on. We're talking about the numerator, right?
No, I'm sorry. Okay.
Oh, I see. You were doing the denominator. Okay.
Yeah, I was doing that part first.
About the numerator first. I like working from top down.
Okay.
Okay. So how do I do -1 plus 1 over root 3? Don't worry about rationalizing. What's the common denominator?
It's root 3, so you could put negative root 3 over 3.
Negative root 3 over root 3 is the equivalent of -1.
Yeah.
Now I got a common denominator, so
You can combine the terms.
so I got 1 minus root 3 in the numerator and root 3 in the denominator. Now do the bottom.
And then the bottom becomes 1 plus 1 over root 3.
Okay, now do the math on that. So here's where I'm at. Here's my numerator. And now combine the two bottom fractions. Because I can't flip and multiply until I have a single rational quotient in the denominator.
That becomes root 3, 1 plus root 3 over root 3.
Now, I can flip and multiply, but there's another little shortcut you can do here. If your two denominators are the same, you can just cross them out, and my answer is 1 minus root 3 over 1 plus root 3, which is what you get if you flip and multiply also.
Okay.
The only bad thing about this little shortcut is that if the numerators are the same, you can't do it. You can only do it if the denominators are the same. If your numerators are the same, then you can cross them out, but then you have to flip everything.
Mm-hmm.
The easier way, if your numerators are the same, just go ahead and flip the denominator and multiply and be done with it. But this does save a little bit of time when you've got same denominators here.
Okay.
Okay? All right. So, and that's the answer they're looking for. For the tangent of 23 pi over 12. Yeah, it's amazing. You truly can learn to think in radians when you can do these without converting to degrees. I thought I was good at thinking in radians, but not so good. It would have been hard. This is pi over 6. This must be some number of, that's got to be, let's see, that's 2 pi over 12, so this got to be 21 pi over 12. Yeah, yeah. In other words, I could have broken it up like that, but it's really hard to see because you have two different denominators. And I'm not, in my mind, I wouldn't have immediately known that that is one of your common, that's one of the points on the unit circle that they want you to memorize.
21 pi over 12? Huh.
Well, doesn't it have to be? Because that's 315 degrees certainly is.
Yeah.
In other words, 315 degrees is one of those points on the unit circle, right? That's the equivalent of a 45-degree angle.
So doesn't that just become 7 pi over 4, though?
Yes. That's why it's hard. I recognize it when it's 7 pi over 4.
Oh, okay, yeah. I recognize it as 7 pi over 4, too.
Yeah, figuring out how to divide 23 pi over 12 into these two fractions is what's tough. Much easier to convert it to degrees and then do it, as long as you recognize the degrees on the unit circle. But yeah, 21 pi over 12 is one of your points on the unit circle. Okay, let's move on. What's the next? Next one.
All right, the next one, it wants us to find the exact value of the expression, and the expression is tan 43 degrees minus tan 13 degrees. It's separate, yeah. Divided by 1 plus tan 43 degrees, tan 13 degrees.
So notice they're giving you the right side, and you got to figure out what the original was.
Okay.
See, in other words, you got to recognize that you're looking at this sum and difference identity for tan. Right? Because in the top we've got a tan plus or minus a tan, and in the bottom we got a 1 opposite sign tan times tan. So what I'm going to have over here is sum A. Is it plus or minus sum B?
It is minus because the top sign you keep.
Correct. So it's what?
Tangent 30, right?
Yeah. In other words, it's the tangent of A, which is that, minus B, which is that. So it's tangent of 30. What's the exact value for tangent of 30?
Pi over 6. Tangent pi over 6. It would be...
When we take trig functions of angles, we get ratios.
Yeah. It would be root 3 over 1. No, 1 over root 3.
Okay.
Okay, the next one is sine 15 cosine 75 plus cosine 15 sine 75.
Notice they reversed it. Okay, that's fine. They mean the same thing. So what identity is this going to equal to?
Sine A plus B. And that becomes 15 plus 75 equals sine 90. And that becomes 1. Just 1.
Remember the technique I taught you for figuring out the quadrangles?
No. Sorry.
Coordinate of that point right there is 1, 0, correct?
Yeah.
Coordinate of that point right there is 0, 1.
Yeah.
First digit is the cosine. In other words, the x-coordinate is the cosine. The y-coordinate is the sine.
Yeah, I remember that.
Sine of 90 degrees, it's got to be 1 right there.
That's actually the method I used.
Yeah, that's a good method to use, actually. The other method is just to memorize the curve, which you kind of have to do anyway. In other words, you're not getting away without memorizing the sine curve. You're not getting out of trig without memorizing it. And
what is the sine curve?
what I just drew here.
Oh, okay. I think
The graph of the sine function is what I meant. Okay, same with the cosine. you're going to have to memorize the cosine at some point in time. Well,
Yeah, we had our.
once you've memorized those two graphs, well, then these quadrangles become easy, because that's 180, that's 90, that's 270, and that's 360. So the sine of 0 is 0. The sine of 90's got to be 1.
Uh-huh.
It's actually easier. I don't use the method. I don't use that method right there myself. I've worked with Trig so much that I know how to draw the two curves instantly, backwards, forwards, and upside down. And so whenever I'm taking a sine or a cosine of one of the quadrangles, I always refer to the curves, the graphs.
Yeah.
Rather than that technique. But this technique's pretty cool also. If you don't have the graphs memorized, this technique works really well for all four quadrangles.
Both are good visuals.
Yeah. All right, what else?
Okay, so the next one, it is to simplify each expression.
Okay.
So the first one is tan of 2 theta minus tan of theta all over 1 plus tan of 2 theta tan theta.
Okay, and what is this going to be?
Tan.
Yeah, and when I say that, I mean that's the identity for the sum and difference for tan. That's what that's what you need to recognize. In other words, if you just gave this to somebody and you weren't in this topic, they may not, they'd look at that. Not everybody would recognize that that's the sum and difference for tan.
Mm-hmm.
So, what is it?
Tan of 2 theta minus theta.
Which is?
That just becomes tan of theta.
Correct.
And that's not a findable angle, is that?
No.
Okay, cool.
What was the question here? This was not obviously find the exact value.
No, it said simplify each expression.
You've simplified it. This is what it is.
Okay. So the next one is...
Incidentally, the tan of 2 theta minus the tan of theta is not the tan of 1 theta.
Okay.
The numerator itself is not the tan of theta. I can't operate on those two. When I have different arguments, then I just got the tan of 2 theta minus the tan of theta. Now, if I had 2 tan of theta minus 1 tan of theta, then I can operate. As long as the angle's the same, then that's equal to the tan of theta.
Okay.
Just pointing that out. Okay, what else?
Next one is cosine of x, cosine 2x plus sine x sine 2x.
What's that going to be equal to?
Cosine x minus 2x. Because you keep the sign, or you flip the sign, right?
No, you're right. I'm just, it doesn't matter. That's why. In other words, why is it not the cosine of 2x minus x? Because
x is sorry.
I can write this like this. These are identical.
Oh, I don't know then.
The top, well, that was my question when I first looked at it. In other words, that's exactly the same as that. The difference is that this one gives you the cosine of x. the first one gives you the cosine of minus x.
Mm-hmm.
They are the same. Cosine of x equals the cosine of minus x. It is an,
It does?
yeah, it's an even function. Cosine is
Huh.
even, and therefore it follows the convention that the f of minus x equals f of x. All even functions are like that. And if you
Huh.
look at the graph, you'll see that that's exactly what happens. If I go on the other side, notice that if I take the cosine of that point right there, I get that value. Well, if I take the cosine of that negative angle, I get the exact same value. It's an
Okay.
even function, which means it has symmetry with the y-axis, which cosine does. Sine,
Oh, okay. I see.
sine would not be the same. Sine of x is not equal to the sine of minus x, nor is tangent. Both sine and tangent are odd. So the sine of minus x is always equal to minus the sine of x.
Huh. Okay.
Okay? And that's kind of important here. I guess. I mean, if you'd have put cosine, you'd have been tempted to put cosine of minus x, right? Because originally the way you did it was you did x minus 2x.
Yeah.
And you wouldn't lose points. You'd get it correct, but you'd also get it correct if you put cosine of x.
Oh, okay.
Only because it's cosine. I would not be able to do that if it was sine. And it wouldn't come up. In other words, notice the sine identity is sine times cosine, same sign. In other words, plus sine times cosine.
Mm-hmm.
This problem wouldn't come up where you're switching them, like I was able to do here.
Yeah, okay.
Okay, I hope I haven't confused you.
No, no, I
The
get
reason
that,
I
yeah.
was a little confused is because I haven't dealt with that before. I haven't actually noticed that before. That you were coming up with cosine of minus x, and I realized, well, I could switch them around and come up with cosine of x. How can you come up with two different answers? That's only because cosine of minus x is the same as cosine of x.
Mm-hmm.
All right,
Okay.
what else you
Okay, the next one is a word problem.
got? Okay.
So, an electric circuit contains a capacitor, an inductor, and a resistor. The voltage drop across the inductor is given by...
One moment. My tablet
Okay.
went out. I got to unplug it, plug it back in, and
Oh, no worries.
I can't chew gum and walk at the same time, so I can't listen. And hold on, I got to see to plug it back in now. I don't have good enough light. All right. That
No
should
worries.
solve the problem. No, I got to close it out and reopen it too.
Huh.
Yeah, it's just a flaw that happens every now and then with the
Yeah,
program.
understandable.
Just a second. Okay. All right. Sorry. Capacitor.
Okay.
Yeah. I heard your first
So,
sentence, but
yeah, no worries. I'll just restart. So, an electric circuit contains a capacitor, an inductor, and a resistor.
okay.
The voltage drop across the inductor is given by V of L equals IWL cosine WT plus pi over 2.
W, I believe,
W,
is omega. Oh, no,
yeah,
okay, no, we'll do it this way. WT over pi over 2,
WT plus pi over 2.
all in parentheses,
Yeah.
like that.
Mm-hmm.
All right. In other words, this is this is going to be a sum and difference problem.
Yeah.
We
It says,
you don't need to know anything about electricity. Don't let it fool you.
okay. It says where I is the peak current, W is the frequency, and L is the inductive, and T is the time. I'm not sure if that's important information, but
Don't think it is. It's kind of confusing because it's a whole bunch of variables that you don't know about.
Yeah.
What do they ask?
So it says oh, sorry.
What do they want to know?
So it says use the cosine sum identity to express V of L as a function of sine WT.
Okay. Let's do it. What's that turn into?
That becomes, oh gosh, okay, cosine WT cosine pi over 2 plus
Minus.
oh, sorry, minus, it's flipped. Minus sine WT sine pi over 2.
Now, what's cosine of pi over 2 equal to?
0.
Okay, which wipes out that whole part. So we got our answer. What's sine of pi over 2 equal to?
I'm sorry?
What's sine of pi over 2 equal to?
Sine of pi over 2 is equal to 1.
Okay, so it's IWL times minus sine of WT. And the minus sign, that's the minus sign where it came from.
Okay, I see.
In other words, I'm taking this minus sign and putting it in front of the IWL.
Mm-hmm.
Which I can always...
That's not that bad.
No. Yeah, so other than all the strange variables, so all you really had to do was apply the sum and difference and then convert.
Yeah.
In other words, the only reason you can do it here is because the cosine goes away, both of them.
Yeah, okay.
If this was pi over 4, you wouldn't be able to convert it to just sine. Because now we'd have the cosine of pi over 4, which is square root of 2 over 2 times cosine of WT. The only reason we can convert it to a function exclusively in sine is because it happens to be pi over 2.
Okay.
Be added. Okay, what else?
So the next one wants to write each trigonometric expression as an algebraic expression.
Okay.
So it is cosine of sine to the -1 power x, so inverse sine.
That's inverse sine, right?
Yeah. Plus inverse cosine 2x.
Like that?
The parentheses goes around the sine and the cosine.
Okay. I thought that probably had to be the case because I wasn't going to be able to figure it out the way what I was looking at.
Mm-hmm.
Okay, now remember how we did this problem here. Remember what we did? What was the first thing we did? Not the top problem, but the middle problem. Called this theta. That's always the first step, is to recognize that that's an angle. Okay?
Okay.
Once I recognize that that's an angle, I know I'm taking the tangent of theta, and then I can draw a triangle, label theta, label it because the sine is 37.
Okay.
And then this has got to be square root of 40. Now I can figure out the tangent of theta.
Mm.
Going to use a similar strategy for this problem. And the strategy is, well, that's one angle. This is a different angle. So let's call that delta? Not delta. What? That's not sure what Greek. Believe it or not, I'm a math tutor for 8 years, and I still don't know the Greek alphabet very well.
Oh, that's okay.
Let's call these angles alpha and beta. I know
Okay.
there's alpha and there's beta. Those
Mm.
Greek letters are usually used for angles, whether it's theta or delta or alpha or beta or phi. Just a Greek letter usually means an angle. Well, now we got cosine of alpha plus beta.
Mm-hmm.
What's that going to become?
The alpha of the sine of A would be x over 1.
Hold on. Yeah, I think you're a little ahead of me here, a little out of order.
Okay.
Let's first of all use the sum and difference formula to rewrite this. In other words, what we're looking at is the cosine of alpha plus beta, right?
Okay, yeah.
In other words, let's start here.
Okay.
What's that equal to?
Cosine
We're
A.
probably going to have to do what you were doing. You were just doing it in a different order than me.
So kind of distribute out the, or like expand it in a sense.
Let's first of all write it like this. Okay. Now, what's the cosine? Well, now we do have to do the triangle. Label alpha, which makes x over 1 and makes the hypotenuse what?
X squared plus 1. Or 1 plus x squared.
Square root of x plus 1. Remember, always start your answers out with square root of. Even if it turns into a number, always remember to start your answer out with square root of. Whenever you're solving for any side in a right triangle. Okay?
Okay.
And then I got another triangle for beta. A different triangle. And beta, the cosine, is 2x over 1. We didn't do the first one right. I didn't do it right. You didn't give me the bad answer. 1 goes there. Right?
Mm-hmm.
Which makes this the square root of 1 minus x squared. Now we're correct. And what's the side opposite beta over here?
Square root of 1 minus 2x.
Minus 2x squared.
2x squared.
Which is 4x squared.
Wait, why is 2x squared 4x squared? I'm confused on that.
Now, there's a difference. These two are not the same, as what we really are doing is this. Remember, it's the square root of the hypotenuse squared minus the short side squared. Well, the short side is 2x, so we have to square 2x, the quantity 2x. And when you square 2x, you get 4x squared. You gotta square the 2 and the x.
Okay.
Okay. So now we have our two triangles, and that's going to allow us to answer each of these What's the cosine of alpha?
The cosine of alpha is square root 1 minus x squared over 1.
Which I can write like that. What's the cosine of beta? Well, we know that's 2x, right?
Then the sine of
I don't have to
A,
do any math to figure out the cosine of beta. They basically give it to us up here. We do need these triangles, though, to get this cosine of alpha and to get sine of beta. So I'm going to subtract the sine of alpha, which has to be x, times, what's the sine of beta?
The sine of beta is root 1 minus 4x squared.
So that's got to be your answer. There's nothing I can do. I cannot factor out anything. I could factor out an x. So I could do this. X time, in other words, our final answer. But generally, my general rule with factoring is that only do it if the problem either calls for it or there's something else you can do. In other words, if I've got a denominator that's got an x in it, well, now I definitely want to factor out an x because I can cancel it with the denominator.
Okay.
If I can't do anything different with the answer, then I think that answer is as good as anything I can write. I certainly can't multiply the x times the square root of 1 minus 4x squared. I can't take anything out of that radical sign, or no, I can't. Let me think for a moment. No, I think this is the final answer. Do you have answers on these, by the way?
No, unfortunately.
I would go with that. I don't think you'd lose any credit. Even if I could change it, I could certainly factor an x out and write it differently, but doesn't change the answer, doesn't really make it a better answer.
Okay.
So that's as good as anything. Yeah, and I can't multiply the 2x times that either. So, all right. The key difference on this problem from every other one we've done is that there's two angles and two triangles that you have to draw.
Okay.
All right. What else you got?
The next one is, so this one's kind of big. Sine of inverse sine root 3 over 2 minus inverse tangent of x.
Okay, what's the first thing I want to
do? Either label them alpha and beta or draw triangles.
Yeah, I like this step first.
Okay.
They're different angles. And in fact, I don't need to draw a triangle. I could actually solve for alpha because it's one of the common ones. That's 60 degrees. But let's leave it as this. I don't think there's ever a reason in any of these problems to actually solve for alpha or beta. Instead of drawing the triangle first, let's go, all right, I'll draw the triangle. Doesn't matter what order you do these in. Label the triangle.
Root 3 is on the far side, or no, root 3 is on the, yeah, no, root 3 is on the far side. And then 2 is on the hypotenuse.
Yeah, that's the opposite side. In other words, if you want to talk about this, it's the side opposite alpha.
Yeah.
Okay? And the other triangle?
The other triangle, x is on the cosine, and, sorry, x on the cosine. X is on the adjacent side, and 1 is on the, or no, x is on the far side, and 1 is on the adjacent side.
X is on the opposite side, 1's on the adjacent. What's the hypotenuse?
The square root of 1 plus x squared.
Over here, the third side is 1.
Okay.
Okay, just applying the Pythagorean theorem. So
Yeah.
now let's use the sum and difference formula.
Okay. It becomes sine A cosine B minus sine B cosine A.
Now let's fill in for everything. What's the sine of alpha?
Root 3 over 1.
Root 3 over 2.
Root 3 over 2.
From either reading the triangle or this.
Yeah.
Okay, what's cosine of beta?
1 over root 1 plus x squared.
It's the sine of beta.
Sine is, sine of beta. X over 1 plus x squared, root 1 plus x squared.
And the cosine of alpha?
1/2.
The only reason we need to draw these triangles is because we don't know the cosine of beta or the sine of, or the cosine of alpha. In other words, we know what the sine of alpha is. It's root 3 over 2. I didn't need to draw the triangles to know that. I know that from looking at that. Now, this one, I'm not going to be able to figure out either the sine or the cosine of beta without drawing the triangle. In other words, I did need to draw the triangle because I don't really know how to figure out the sine of beta or the cosine of beta.
Yeah.
There's really 3 things that we had to figure out. The only one that I was really given was that one there.
Yeah.
Okay.
Okay, the next one, 29, is tangent of inverse cosine -1, or inverse cosine x plus inverse tangent x.
Okay, tell me everything to do.
First, label alpha and beta. Cosine alpha, tangent beta.
It's not cosine alpha.
I'm sorry?
It's not cosine alpha. That's equal to alpha.
Yeah, that's equal to alpha.
Cosine alpha. Okay, in other words, when you say the cosine alpha, that would be a number, a ratio. Well, we're looking at angles here, and part of this whole process is recognizing that this is an angle and that inverse cosine of x is an angle. inverse tangent of x is an angle.
Mm-hmm.
So I suppose we can do this. We'll draw the triangles first. Dimension the one on the left.
So alpha becomes, the adjacent side is x, the hypotenuse is 1, and the opposite side becomes root 1 minus x squared.
And notice why we're going to need that opposite side. Because I'm dealing with tangent, and the tangent sum and difference formula is all tangents. Right?
Uh-huh.
There are no sines and cosines in it. So I'm going to need the tangent of alpha and the tangent of beta. Well,
Okay.
I know what the tangent of beta is. It's x. Let's go ahead and label that. Don't really need the hypotenuse. You'll see why. So what is the tangent of alpha plus beta using the sum and difference formula equal to? Here, I'll do it up here so I have room. So it's what?
Tan A plus tan B over 1 minus tan A tan B.
And now fill in. What's tan A?
Tan A is, oh wow, okay, so it's root 1 minus x squared over x.
Can't simplify that. What's tan?
Plus x over 1, so that's just x.
Okay. I'm going to go ahead and write it as x squared over x. Same thing as x, only now it's a common denominator, and I'll be able to add those two together.
Over 1 minus root 1 minus x squared over x times x squared over x.
You know, this time I don't really need to make it x squared over x. It'll complicate matters if I do it in the denominator. I mean, not complicate them seriously, but you see why it's easier to just write it as x? Because I'm going to be multiplying these two. So the x's disappear. Now, we do want to simplify this because it might simplify. In other words, I definitely don't want to give this as an answer. At a minimum, I can add the numerators together. So the numerator becomes 1 minus x squared plus x squared all over x. Bigger fraction bar. And the bottom just becomes 1 minus square root of 1 minus x squared.
Okay, yeah.
Okay. Now, another thing you can do when you have a situation like this where you have a fraction in top and you don't have a fraction in the bottom is I can just take this x and move it to the denominator as long as I put parentheses around it like that.
Okay.
Which is the same thing I would get is if I put a 1 under the denominator, flipped and multiplied.
Yeah. Okay.
In other words, you end up with that x in the denominator also. Now, is there anything else I can do here? Nope. I don't believe there is. Yeah, there's nothing I can do with this x squared and this x, because this x squared is being added, this x is multiplying.
Uh-huh.
And if I distribute this x in the bottom, doesn't help, becomes x minus x times that, which doesn't match anything up here. In other words, if I distribute it, it becomes x minus x times 1 minus x squared. And if I erase that and use this instead, I can't do anything with it.
Mm-hmm.
No, either that's the final answer or what I had right before I distributed the bottom.
Yeah. Okay.
In other words, I can't really I was looking to be able to do something with that there. If I could get them both as multipliers, I could cancel it out, but I can't. Not.
I see how that works.
So some of these things, when you work through all the algebra, they come down to a real simple, 1/2 or something. Because usually they'll give you these problems where after you do all the complicated algebra, you get stuff to cancel. So it's not such a complicated answer. But if there's a way to do it on this one, I'm not seeing it.
Yeah. Okay.
All right.
Cool.
Nick, I will talk to you next time. Have a good week.
Thanks. You too. Thank you very much.
Yeah. Bye-bye.